Hey, in today's edition, we're taking on titration problems. Specifically, I want to look at the type of question that has a weak acid or a weak base being mixed with something strong. I think these questions are much more common on exams and quizzes, and honestly, they're more complicated, so that makes them deserving of a slow-paced video like this where we go over everything step by step. Now, I'm ready to get started, but first I have a question. Do you really understand the difference between an equivalence point and a halfway point? If you don't feel confident in those as concepts, what they mean, where they are on a titration curve, I encourage you to pause the video here, look at your notes, look up those definitions, and come back to the video because they're going to be key terms I'm using in this problem-solving strategy. All right, but assuming that you're ready to go, I know I am, so let's learn how to solve titration problems together. What's up, everybody? Welcome to Neil's not-so-boring world of chemistry. Let's go into the lab and take a deep look.
Okay, so before we get into the problem solving, I just ask that you pause the video here and read through the question thoroughly. So we have propanoic acid, and that's a weak acid being titrated with a strong base, sodium hydroxide, and we're given the concentration of that sodium hydroxide. They also tell us the Ka of our propanoic acid. We're actually not going to use that number in part A, but it will be important for part B. Now in this experiment, we have 25 mLs of the strong base, and it's required to titrate a volume of 40 mLs of the weak acid with an unknown concentration to its end point. And basically, they want us to calculate the concentration of the propanoic acid. Now, very quickly, what's the significance of the end point? So a quick reminder, the end point is when your indicator changes color, and it tells you that you've reached the equivalence point. I know we have a lot of points here. The equivalence point is when the moles of acid are equal to the moles of the base. That's critical, because that means we can calculate the moles of the base using the volume and the concentration, and we then know how many moles of the acid we have at that endpoint. Okay, so again, they want us to find the concentration. What's our approach going to be? Well, I think you know that concentration, molarity, is calculated using two values, moles divided by volume. Now you can see here next to the word moles, I put a question mark, because I don't know how many moles of the weak acid I have. That's not given in the question. So in green, I wrote use stoichiometry. That's how we're going to get the moles. Now next to the word volume, I wrote 40 mLs, because you can see in the upper right-hand corner, that was given to us in the question. Now in parentheses, I also went ahead and converted the 40 mLs into liters, simply moving the decimal 3 places to the left. Okay, but let's focus on that stoichiometric step because we need to find the moles of the weak acid. So here's the reaction that we're concerned with in this particular problem. We have our weak acid. It's going to react with the NaOH. Now the only part of the NaOH that's of any significance to us is the OH minus. Na as an ion isn't really going to do anything. And it's going to form water, and it's going to form the conjugate base of the propanoic acid. In other words, the OH minus takes a hydrogen off of the propanoic acid, forms water, and then we have this negatively charged polyatomic ion as the conjugate base, right? Okay, now remember, we need to find the moles of the weak acid. Well, again, because we're at that equivalence point, we can find the moles of the strong base. And we're going to do that using the volume, and you can see I wrote the word given because 25 milliliters is given to us in the problem. See it up there in the upper left? But I just converted that to liters. And I also know the concentration of the NaOH. It's 0.100 molar, and that can also be written as 0.100 moles per 1 liter. Same thing. So doing this simple calculation, I find that we had 0.0025 moles of OH minus. Now remember, the moles of the acid are going to be equal to the moles of the base, and we just found the moles of the base. So we know that because there's 0.0025 moles of OH minus, there must also be 0.0025 moles of the propanoic acid, because those two molar amounts have to be equal if we've reached the equivalence point. And we know we're at the equivalence point because we're at the end point. So now I'm going to take those moles of propanoic acid, I'm going to divide it by the volume of propanoic acid. Now again, we were given that, right? They told us we had 40 mLs of the acid at the end point. I just converted it to liters, so it's 0.040 liters. Moles of acid divided by volume of acid gives us our concentration of the weak acid, which is 0.063 molar. Now we're ready for part B, so please pause the video and read through the question. So you'll see in this second experiment, we have 60 mLs of our weak acid, and this time we know the concentration of the propanoic acid. They're asking us, how many milliliters of the strong base would you need to titrate the solution to its equivalence point and its halfway point? So in that first part of the question there, they want two different volumes. And then they say, what is the pH of the solution at the equivalence point and at the halfway point? So there they want two pHs. So really, this is like 4 questions. Okay, let's start off with the milliliters of strong base needed to titrate the solution to the equivalence point and halfway point. We'll do that first. Now, our approach is going to be, we're going to use stoichiometry. We need to find a volume, right? So we need to have an answer in milliliters or maybe liters of the NaOH needed to provide an equal number of moles to the number of moles of the weak acid. Remember, that's what's equivalent at the equivalence point, right? Now, once we get that volume, we can just divide that in half, and that'll tell us the volume required to get to the halfway point, so that's super easy. All right, so let's get to the stoichiometry. Now, you can see here in green, I have the stoichiometric calculation written out for you. Why am I starting off with 0.060 liters? Where'd that number come from? Well, that was given in the problem. You'll see up top that they wrote it as 60 milliliters, so I just converted to liters by moving the decimal, and I'm multiplying that by the concentration of the weak acid. So again, 0.15 moles of propanoic acid over a liter is just another way of writing this. And this was given to us in the problem, okay? So by doing this first part of the calculation, I'm really finding out how many moles of the weak acid I have at the equivalence point. And now I'm going to say, well, for every 1 mole of the weak acid, there should also be 1 mole of hydroxide, which comes from the strong base. Okay, why is it 1 to 1? Well, I'm going to go all the way back here to the first problem we solved and look at this balanced equation. Do you see on the left side of the arrow, for every 1 mole of propanoic acid, you have 1 mole of the base. So it's 1 to 1. So I'm really drawing on that balanced chemical equation to get this ratio here of 1 to 1. 1 mole of OH minus to 1 mole of propanoic acid. So when we do that, that kind of takes the moles of the weak acid and converts it into moles of the base. But remember, we don't need moles of the base. We need a volume. So how do I go from moles to volume? Well, I'm going to use the concentration of the strong base. So it says 1 liter over 0.100 moles of OH minus. That's just the concentration of NaOH that was given in the problem. It's just another way of writing it, right? So I took the 0.100 molar, which is the same as 0.100 moles per liter, and I just inverted it here. Now, why did I do that? Well, it was intentionally because I need liters to be the unit of my answer. Remember, we're trying to solve for a volume. So I can take that moles per liter and flip it upside down so that my answer will be in liters. So doing all this math, and I really do suggest you punch it in your calculator so you see how it all works out, I found that we have 0.090 liters of the NaOH. In other words, we need that volume of NaOH to give us the same number of moles as the moles of the weak acid at the equivalence point. Now, if I just take that number, 0.090 liters, which by the way is the same as 90 mLs, and I just divide that by 2, that's the volume to get to the halfway point, 0.045 liters of sodium hydroxide. because the halfway point is half the volume required to get to the equivalence point. So our answers for the first part of this question are 0.090 liters of NaOH to get to the equivalence point and 0.045 liters of NaOH to get to the halfway point. All right, now let's get into the pH part of this problem. So now we're ready to deal with the pH portion of this question. And I would like to deal with the pH at the halfway point first, just because it's a bit easier and more straightforward. Now, by definition, at the halfway point, we know that the pH will be equal to the pKa. Now, we were given the Ka back in the original problem. You may remember it was 1.3 times 10 to the negative fifth. So here you'll see I've taken the negative log of that Ka value to get the pKa, which is 4.89. And that means that that's also the pH at the halfway point. Okay, so the only thing remaining is finding the pH at the equivalence point, and this is going to take quite a few steps. So firstly, we know that at the equivalence point, all of the weak acid and all of the strong base have reacted with each other because, again, they're equivalent in terms of molar amounts. So there should be no weak acid left and no strong base remaining. But we also have to remember that as the weak acid is reacting with the strong base, it's making its conjugate base. It's not making the NaOH, that was the strong base. It's making the conjugate base of the weak acid. So we're going to have to ask ourselves, how much of that conjugate base is in the solution? Because it's that conjugate base that's going to determine what the pH is. So here you can see I've set up a simple equation to represent what's happening at the equivalence point. We have the conjugate base, which is the negative ion, reacting with water, and it's going to make some more of the weak acid, and of course, some OH minus. Now, we're going to need to ask ourselves, what's the concentration of that conjugate base at the equivalence point? And in order to do that, we need to do the following. At the equivalence point, all of the moles of our weak acid, HC3H5O2, propanoic acid, have been converted into moles of the conjugate base. Now, we can figure out how many moles of the weak acid we had, and therefore we can then figure out how many moles of its conjugate base we have. So you'll see I've done a calculation here where I'm taking the volume of the weak acid, which was given to us in the problem as 60 mLs, I've just converted it to liters, and I'm multiplying that by the molarity of that weak acid, which again was given to us in the problem as 0.15 molar, and I've just written it out as moles per liter. And I find out that we had 0.009 moles of the weak acid. So that means all 0.009 moles have now been converted into the conjugate base. But we need the concentration of the conjugate base. So we also have to take into consideration what's the volume of the solution at the equivalence point. Okay, at the equivalence point, we added a bunch of base and we had the original volume of the acid. So I need to combine those two numbers, the 90 mLs of base plus the 60 mLs of the acid. Now again, in this calculation, you can see I've converted them to liters by simply moving the decimal. And now I can take the moles of the conjugate base divided by the sum of the two volumes, and I get a concentration of 0.0600 molar of the conjugate base. So now we know how much of that conjugate base we have present at the equivalence point in terms of its concentration, and we're ready to do an ice table using that value. So back up here, I've now taken that 0.0600 molar that we just calculated and entered that as the initial concentration of the conjugate base. Now some of that is going to turn into the acid and some of it's going to turn into OH minus, and we're representing those amounts as X's. And now we're going to use an equilibrium expression. But because this is a conjugate base, we're going to need a Kb value. Now you may remember in the problem they gave us the Ka of the weak acid. So how do we get a Kb if we know the Ka? Well, we need to remember that Kw is equal to Ka times Kb. So we know the Ka, that was given to us, and Kw is always 1 times 10 to the negative 14th, unless of course they tell us it's at some odd temperature, which they haven't. So we can solve for the Kb. So Kb will be equal to the Kw divided by the Ka, and you can see I've set up the math there. And I find that the Kb is 7.7 times 10 to the negative 10th. Okay, so now I can take these values for the equilibrium concentrations from my ice table and set them equal to this Kb that we found. So here's what the equilibrium expression looks like with the products in the numerator and the reactant, which is the conjugate base in the denominator. And I'm going to set that equal to the Kb. I'm going to eliminate the x in the denominator because it's considered to be an extremely small number and not relevant. And now we're going to solve for the value of x. Doing that, I have x squared is equal to 4.62 times 10 to the negative 11th. I take the square root of both sides, and I find that x is equal to 6.8 times 10 to the negative 6. And of course, I encourage you to do these calculations in your own calculator as we go through them. So x is the concentration of OH minus. Now remember, let's refocus. We're trying to find the pH here. So how do I go from a concentration of hydroxide to a pH? Well, I can find the pOH by taking the negative log of that OH concentration. And you can see I've done that and I find it to be 5.17. Now another thing we know to be true is that the pH added to the pOH will always equal 14. So in other words, if I take my pOH that I just calculated, 5.17, and I subtract it from 14, I can find my pH, and the answer is 8.83. Please take a moment to read through the question. Pause the video and work through the problem trying to come up with solutions of your own. Then continue watching for a step-by-step guide on how to get the right answers. So here we have a weak base situation where there's 90 mLs of a 0.6 molar ammonia solution. We're given the Kb, and we also know that the acid we're using for titration is HCl and it's 1 molar. We're going to find the starting pH of the base, the volume of acid needed to reach that equivalence point, and finally the pH at the halfway point. Part 1, what's the starting pH of the base? You'll see that we have to consider the reaction of the weak base and set up an ice table. Now because we're given the Kb, we can set up an equilibrium expression and set it equal to 1.8 times 10 to the negative 5th. We can solve for x, which will represent the concentration of hydroxide. Then we can take the negative log of that number to get the pOH, which is 2.5. Now, of course, the pOH combined with the pH must equal 14. So by subtracting 2.5 from 14, I find that the pH is 11.5. For question 2, we need to find the volume of acid needed to reach the equivalence point. Now, the volume of the weak base is given as 90 mLs, and I've converted it to liters. I'm then going to multiply that by the concentration of the weak base, which was given as 0.06 molar, and I've just written it as moles per liter. And I find that we had 0.054 moles of the weak base. By definition, we need an equivalent number of moles of HCl at the equivalence point. So how much HCl solution are we going to need to get 0.054 moles? Well, I use the concentration of HCl, which is 1 molar. I invert it as 1 liter over 1 mole of HCl, and I find that the volume required is 0.054 liters of HCl. Question 3, what's the pH at the halfway point? Well, as you can see, I've written a version of the Henderson-Hasselbalch equation, which says that the pOH will be equal to the pKb plus the log of the concentration of the conjugate acid divided by the concentration of the conjugate base. Now, because we're at the halfway point, the concentration of the conjugate acid and base will be equal. Therefore, we can eliminate that term in our expression. So we're left with pOH is equal to pKb. So the pOH will be equal to the negative log of the Kb, which is given in the problem. And I find the pOH to be 4.74. Now again, that combined with the pH has to equal 14. So by using subtraction, I find that the pH at the halfway point is 9.26. Thank you for watching. I hope you found this video to be helpful, and I look forward to seeing you in the next edition.